welcome everyone to another edition of the Finite Element Seminar at LNL. This is the last seminar for the year. We've had a great year, 14 different talks. We're going to continue strong next year, so please come back after the holidays. It's our privilege today to have Professor Dr. Martin Kronbichler. He's currently in the Ruhr University in Bochum. Before that, he was at the Technical University in Munich. We've known Martin for a long time. He's doing really excellent work in High-Order methods, in deal.II. That's what he's going to talk about today. And always really impressive talk. So I'm looking forward to what you have to present, Martin. Thank you for coming. The floor is yours.
Okay, so I'm very happy to welcome you to my talk. I'm going to talk about fluid flow simulation and high-order methods with the deal.II library, and I'm going to focus on several aspects in our research that we do in our group. This is joint work with many people. I listed the most important ones here, but of course we have a large community and we have many contributors. So I'm really not just talking on my own behalf, but I have many people that I've been working with on these topics. So let me just start with a few words on the applications and just give you some small insights, even though this is, of course, far from comprehensive. We've been looking into various different scenarios in the past years, and we are continuing to looking into those. So we're having looking into turbulent flows in various aspects. So typically when you think about turbulent flows, there's different setups here, of course, compressible, incompressible flows. I'm just considering one of those. Where the challenges is mostly on Poisson problems, where you use multigrid methods, but there is a few more challenges in these applications as well. We've been looking into coupled flow, especially in the biomedical application side. So you see a human lung in the middle of my screen here, where we have been doing some work in the past years and have a lot of new projects going in this direction. And then we also have kind of coupling to acoustics and similar effects that you see on the right. So let me just quickly talk about this model that we're going to consider. So we're looking into incompressible flow, which is governed by the Navier-Stokes equations, and I just want to quickly focus on this system here. So we have velocity u, we have a pressure p that we're solving for, with some right-hand side forcing possibly. We have the divergence-free condition. So this is a typical saddle point problem, and we are going to look at this in 3 dimensions primarily, where you need a lot of resources. And of course, the question that people ask in Navier-Stokes equations, both compressible and incompressible, there is always the question of using a finite solution where you kind of physically resolve all relevant scales of the flow, or you're doing some coarse graining and you want to wonder how good this approximation is going to be. And of course, the pictures that you see here on my screen are the simple ones, in the sense that you can still represent them easily on a moderate sized machine. You don't even need a supercomputer for those figures. But the question is, of course, when you go to real flows on larger Reynolds numbers, then you're going to be more and more towards the application side. So let me just come to my first topic here. I want to talk about some robustness and some of the research that we did here, because I think this is an interesting field in terms of finite element methods and discretizations. So we're looking into discontinuous Galerkin methods because when we think about the transport phenomena, we really would like to use the upwinding. I will give a few more arguments later, but just quickly for those coming from different discretizations, discontinuous Galerkin methods, they use a mesh of elements. You put polynomial solutions on each of the elements, and you don't impose the continuity. So here on the right of my screen, I just inserted a scalar problem, which I visualized. I mean, this is a kind of classical transport diagonally through the domain. It does a lot of overshoots. So this is not even a perfect discretization for this kind of problem, but I just illustrate the kind of solution fields that you might get with the DG method. When you do DG methods, you use a weak form like the finite element method. So in case we use the transport equation in 1D now, as an example here, we would just integrate over the domain. We would integrate by parts eventually, and then for integration by parts, we get the boundary integral, and the boundary integral, we use this to connect the elements. So of course, in DG methods, you don't have continuity over the element. So formally, you can only do the integration across a single element. So the connection that needs to come into the numerical flux, which I write as A times U star, where A times U star could, for example, be upwind or any other scheme that people have developed during the past 3 decades in the DG method, or even longer back when you also consider finite volumes which have similar ingredients. So this is the next, this is the main ingredient, and you see that, well, essentially the method works. I mean, of course, there is always the question about exactness of these methods, but this is where we use as a starting point. Now we can go to the Navier-Stokes equations. I write the Navier-Stokes equations kind of in a similar form as you saw on the discrete form. Of course, I now introduce operator. We have the mass operator with the time derivative of the velocity, and we have the convective operator, which uses this divergence of u times u. So this is a nonlinear term, the transport of the velocity field with itself. Then you have the viscous term, so just a classical Laplacian or vector Laplacian on the velocity. And then we have the pressure gradient as the last term here, then some right-hand side. And then we have the divergence-free condition on u with the test function of the pressure space. So essentially, this is a classical weak form. The ingredients that we use for the DG discretization are very classical in the sense that we could just list them one by one. For the convective operator, we just look into local Lax-Farigis fluxes, which is just integrating by parts, and then you get the kind of the jump, and so kind of you get the jump of the velocity times a penalty parameter, which is typically the norm of the velocity in normal direction. You also get this kind of divergence, the u times u term. So this is the average flux here. So essentially, this is a very classical one, not even the most sophisticated one. You could use some row fluxes or some more energy conserving ones, but it really does not matter too much at this point. So the viscous operator maybe is a bit more interesting, because when you think about second derivatives in DG methods, then often people reformulate the problem as a system of equations. So essentially, instead of having just the gradient, the velocity, you also introduce the gradient. So the velocity gradient as an additional variable. Of course, since we have a 3D velocity, the gradient would be a 9-dimensional object. So this adds to the equations, and especially in higher Reynolds number flows, this is scaled by the viscosity. Viscosity is like 1 over the Reynolds number. So this is going to be a very small contribution, and if you just add a system of equations, this would be probably the most expensive term. So I always think that we should use the cheapest method available. And in my opinion, the symmetric interior penalty method is a nice one, because you can, of course, formally derive it from a system of equations, but eventually you do it in the primal form without auxiliary variables, which I prefer, because then it's essentially just classical DG terms. For the last two terms, velocity gradient, pressure gradient, and velocity divergence, we just use central fluxes, which essentially is just using the average of the pressure or the average of the velocity in this equation. Of course, you could reformulate this a little bit, because many times when you do incompressibility, so Stokes equations, you want to have the pressure gradient being exactly the same as the velocity divergence. So you would integrate one of these terms by parts. I just see here that I forgot the dot here. So this is actually nabla times v here. So this is actually the divergence of the test function on the velocity. So this is my ingredient here. I should mention that it's actually not even trivial to do the DG discretization in the right form. We did a paper some 6-7 years back where we analyzed this way, because it turned out that this is not straightforward as you could think, because there is some stability issues when you're trying to solve this with so-called splitting method or projection method, which is kind of splitting the system here that you see as a saddle point form into momentum part, or kind of a part for the velocity, and a split off part with a pressure Poisson equation, which is considered as the most efficient discretization. But I don't want to talk about that too much, because this is known results, you could say. I should, of course, mention that we are using a mesh of elements. Quadrilateral elements is my favorite, or hexahedral elements in 3D is my favorite element type, where you use a Gaussian quadrature formula for computing the integrals and the viscous term, the mass matrix term. You can do this on arbitrary meshes, default meshes. The convective term is nonlinear, so you need more points to compute the integrals exactly. Of course, always with the assumption that you have affine element shapes to do it exact, and otherwise you do some integration error related to the geometry, but they are typically not very sensitive to that. Now, when we applied this to turbulent flows, and now this is a result that we worked on during the last decade, you could say, then you find out that just applying these terms that I've shown you is not working. Of course, people have seen that DG methods are robust for dominating convective terms, so typical transport problems work really well with DG. Of course, they're not oscillation preventing, they don't apply well to compressible Navier-Stokes where we have shocks, for example. You need the additional limiter techniques for that. But in the incompressible regime, you would expect that, well, it kind of should work, but what we realized is that the classical equations for different formulations, they did not work. So you see that the line's exploding, so this is some divergence error, and you see that there is some errors, and at some point it just explodes. Whereas other methods that I'm going to present now, they're actually reducing in the divergence error, which is what you would expect. I should mention at this point here that these equations, so at this point when I talk about divergence errors, you could wonder, how is it coming that I have divergence errors? Because, well, maybe we go back to the original equations, you see the divergence of u is equal to 0. So you would wonder where they come from. Well, the reason is that, well, of course, we use a discrete formulation, and if you just use discontinuous spaces of both the pressure and the velocity, then you are close to 0 with the divergence error, but you're not exactly 0. So this is a discretization error. And you would, of course, expect it to be small. Now there is a strange scaling in this case here because we wanted to refer it to the turbulent quantity. So this is why you see it, even the small error being in the order of 1. But this is just a scaling issue, you could say. The interesting part is that some methods have the order 1 error and the others have a 10 to the 6 and eventually exploding error. Where does it come from? Of course, you can analyze this mathematically. We did this in the past. And when you look at kind of the energy balance, then you would realize, well, of course, there is some numerical discretization error. So energy estimate, you just consider the convective term. You ignore that there is a dissipation in the viscous term, but turbulent flows have very low viscosity. So essentially, it's the convective term that matters. And if you look at the energy balance, we have this red term here, which is the Lax-Friedrichs term or upwind term, you could say. This is the dissipating term because you see that there is the u times u, so a jump in u squared. So this is a nice term. However, there is also this divergence of UH times u squared, and then there is this kind of u plus times u minus. By u plus and u minus, I refer to the solutions on the two sides of a DG element, which is multiplied by the jump in solution. And again, these two terms on the right, they are not definite in terms of the sign, so you cannot really control the sign. You might have discretization errors making these terms positive or negative, and if you have the wrong sign, they kind of can give rise to the energy. So there is a potential as being instability for this reason. Of course, these terms would vanish if I increase the resolution, because the divergence of UH, this is exactly one of the equations. So if I increase the resolution of my discretization, I would reduce the discretization error, and eventually this term is going to vanish. And the same for this one here, the velocity over the element boundary. If I make a well-resolved simulation, then the solution is going to be smooth, and then there is no jump of the solution over the element boundaries or in DG methods anymore. So again, this is a continuous term eventually, so they're going to vanish. The problem is just that in order to make them vanish, I would need something, a resolution proportional to the Reynolds number, or maybe even 10 times the Reynolds number in every space dimension. If I'm doing a 3D simulation with Reynolds 10,000, I would need 1 trillion, 10 to the 12 grid points approximately. And this is a huge supercomputer, and Reynolds 10,000 is not super challenging in practice. I mean, people want to use 100,000 or 1 million, and in that case, it would be completely unrealistic. Now you could say, well, of course, this is just a stupid discretization. This is Lax-Friedrichs in a basic formulation. There is some theory on skew symmetry, which conserves the energy. There is theory on split DG methods. So there is, of course, a lot of theory in there, which is true. The approach that we chose and we find more mathematically elegant is to look at the method as a kind of H-diff conforming finite element space. And what is that one? Maybe let me quickly mention this on this slide here. So in black, we have the 4 terms of the momentum equation, Navier-Stokes, and then we just add 2 more terms, which is kind of a divergence penalty and the continuity penalty term. You see that these penalty terms are just having kind of symmetric forms, so they're kind of self-adjoint forms. When you insert them into the energy estimate, then the test function VH is replaced by UH, and then you see divergence U times divergence U times a parameter tau is going to be a square form, and then eventually this is going to dissipate the energy. So this is a nice term for our energy estimate. And the same you do with the continuity problem that you had before. So essentially, when you look at the 2 violating terms in the energy estimate on the slide before, we just say, well, we pick those such that they are dominated by penalty factors. And then we had an analysis a few years back when we just considered, well, what happens if we do this penalty factor? Well, essentially, we're just making the space approach something like an HDIF conforming space, which exactly fulfills the divergence-free condition. I mean, there is finite element spaces already out there. There is the classic Rabi-Atomar elements on hexahedral shapes, which of course have the velocity space chosen such that the velocity divergence is exactly the same space as the pressure space, and then the divergence-free condition actually results in a pointwise divergence-free field. So you don't have discretization errors anymore if you choose Rabi-Atomar. And what we do here with our penalty terms is similar. It's not exactly the same space as Rabi-Atomar, because Rabi-Atomar is an anisotropic space. It has different polynomial degrees in different directions. We also considered them in our tests in a work here. But the interesting thing is that we are kind of really imitating kind of the normal continuity of the space, which is what Rabi-Atomar does, and we're imitating the divergence-free condition strongly. So essentially, we're just getting rid of the discretization errors in the space. And we found them in a paper when we compared the L2 method with the HDIF method, so kind of having this finite element space with the penalty factors, and the HDIF method. When you apply them to real turbulent simulations, we observed very similar results. So this was a good result. Let me just quickly show you one of the verifications that we're doing. There's a classical stability problem. Actually, it's just 2D. Reynolds number is 7,000, and there is some perturbation field here. So the classical is just a channel flow, but then you have this perturbation, which is much smaller, 10 to the minus 5 compared to the initial velocity here. And then you just look at how the method behaves. On the left, you see the evaluation with the classical approach and the G methods without the penalty terms. You would expect the circle, so there is a linear stability theory which provides you with the expected behavior, at least for small deviations, small times. But when you look at the DG methods, the dashed line and the dotted and the solid line, you see that they're immediately exploding in this perturbation energy. And so this, of course, is wrong. The more interesting thing is actually the finer mesh. The 16 squared mesh is actually exploding earlier than the 8 squared mesh, which is because of there is a fixed amount of time that you need to spend in order to get unstable. But both of them are bad. When you add the penalty terms, so we're adding this kind of constraint to the finite element space, and you see that the coarse discretization, the dashed line, well, it's still far away, but at least it does not grow unboundedly. So you see that there is, of course, an error. This is a discretization error. But when you refine the mesh, go from 8 to 16 elements, then you can eventually resolve kind of this, you can resolve this structure here that you have near the boundary. So with 8 elements, I was just having a 2-course mesh. So it got a bit bad here, but when you refine the mesh, you see that I'm almost perfectly on the linear stability theory. But if I would refine one more time, I would get even closer to the solution. So you see that this is a nice verification. It works well. Let me now go to high order methods, because I had this in my title and I wanted to really show you why we are interested in those methods and what is interesting. Of course, when you think about efficiency of the computation, you want to go towards a low number of degrees of freedom. So every degree of freedom should carry a high accuracy. We want to have methods applicable to general geometries. So we also want to have a mesh-based method, which is flexible, like finite elements, or in our case, discontinuous Galerkin. Now, the point is when you do flows, incompressible flows and compressible are really similar. You develop fine scale features related to the Reynolds number. The higher the Reynolds number, the more fine scale features you have in relation to the global scale of your simulation. And we need to kind of track the solution over a long time. We need good dispersive behavior. What do I mean by that? Well, it's not really the convergence rate of high order methods that I'm out for, but what I'm out for is actually that the high order methods have very good dispersive behavior, in the sense that they're not distorting my profiles when I consider them over a long time. And of course, if I have high Reynolds numbers, the local structures are small, but they are relevant over a long time when they pass through my computational domain. So eventually, they're going to matter a far distance apart from where they originally were created. This kind of behavior is tracked well with high order methods. I told you before that we prefer hexahedral meshes because they have more efficiency. High order methods adding unknowns into the interior of the elements. Now, continuous elements are in this picture here. Of course, the DG method is very similar because everything that is added as a high order polynomial goes into the elements because I have no continuity. And DG methods have the upwind fluxes, which give us some controlled dissipation. I mean, I told you before that this dissipation of the DG method is not really enough to capture the jumps in the solution. So you still have some dissipation, which is coming from the penalty terms. But the main advantage of the dissipation is that we are having the ability of having fine scale features that we don't resolve, and eventually things that we don't resolve, the only option we have is to dissipate them away. This is kind of called implicit turbulence modeling sometimes. When we do time discretization, I mentioned quickly before that we use splitting methods. This is one variant coming from the 1990s by Kaniadakis and co-authors, which essentially just says, well, I pick my Navier-Stokes equations. Now I write them in the strong form before I discretize in space. So I actually say that I do the convective term explicitly in time. This gives me an intermediate velocity u hat. The intermediate velocity u hat after the convective term is not divergence-free anymore. So I need to take the divergence of that term to compute the pressure for a new time step. There is some theory how you choose the boundary conditions when you do the splitting. With the pressure, I can correct the velocity such that the u double hat at step 3 is eventually divergence-free. So this is a nice, the nice field here. And eventually, I do the fourth step, which is the viscous step. So the viscous step is taking into account the viscous effect that we also need to model, of course, in high Reynolds number flows. The fourth step is a very simple operation because this viscosity is a small number, so there is not a lot of viscous effects going on. But eventually, this is your scheme. Of course, when you do the penalty terms, there is a fifth step where I apply my penalty terms, but essentially they follow the same strategy here. If I do Rabi-Atomar elements from the first place, then I would not have this fifth step. I just have these steps here. You can verify this, of course, in Navier-Stokes. You verify it on simple examples. So this is a very simple vortex flow with just sines and cosines as the solution in pressure and velocity, decaying in time. This is very simple. And if you consider the different accuracies of different polynomial orders, that you see that, of course, if I increase my polynomial order, my method gets more accurate and eventually have a steeper slope, both in the velocity and the pressure. I should mention that we use different degrees for velocity and pressure for the reasons of insubstability, or at least easier fulfillment of the insubstability, even though in DG this is not really as pronounced as in the CG method, where continuous elements, where you know the Taylor-Hood theory, and you're completely unstable without it. When you compare high order methods and low order methods, I said before that I actually should not count the elements or the mesh element size, but I should count degrees of freedom. And when I'm adding degrees of freedom into the elements, of course, I have more work to do. So I should account for that by listing the number of unknowns. But even for the number of unknowns, you see that high order methods, in this case polynomial degree 5, which is the black line, is the line which is the most efficient one. It's in the bottom left corner of this graphs here of accuracy error over unknowns. So this is, of course, the desired method in this case. Now, coming back to the actual simulation of high Reynolds number flows, you wonder, well, how is it? In smooth problems, like in this desk problem with cosines and sines, in high order methods we're the winner. But when you consider real flows, you have two things to consider. The first one is that when I do time stepping and I have this explicit convective term. So this is an implicit explicit method. The explicit convective term gives me a CFL condition, and it actually grows with the power of 1.5 with the polynomial degree k. So it actually grows over proportionally. If I choose higher order methods, I need smaller time steps. And if the stability limits my time step, then you do more time steps with the higher order methods. The other thing is, of course, how is the number of degrees of freedom related to the cost of the solvers, especially the pressure Poisson equation. And maybe the most important one is, how is the convergence rate actually? In the simple case, we had this nice rates here, but now let's look at an actual turbulent simulation, even though this is maybe the most simple one. Again, I start with a smooth field, but now I have high Reynolds numbers such that this initial smooth structures decay into a chaotic or turbulent structure. This is a so-called Taylor-Green vortex. I chose polynomial degree 7 here for the visualization. It has 128 grid points in every direction if I just count the number of elements times the polynomials in every element. And you see that there is a lot of fine scale features going on. Then I just check some quantities in this Taylor-Green vortex, essentially some kinetic energy, so U squared, and then there is some metrics like the dissipation of the various methods that you can consider. And then when you look at it here with some reference results of the simulation, and then we choose a Courser mesh, and then you see that, well, for the kinetic energy time derivative, you see that, well, high order methods, which is the solid line, it's a bit closer to the red line than the other two, like the lower order methods. If you check the molecular dissipation, of course, the highest order method, which is polynomial degree 15, is closer than polynomial degree 3, which is the dashed dotted line here at the bottom. But you see that, well, they are actually having all similar trends. But when you look at the convergence rates, so now just considering different meshes for different polynomial orders, I was expecting to get a graph which has kind of different slopes, but you really just see that the slopes are more or less on top of each other. There is some difference of the methods, of course. For very high numbers of degrees of freedom, you see some difference in slope, but this is 10 to the 9 degrees of freedom for a flow which has Reynolds number of 1,600. So this is a trivial flow. And even here, you don't see the asymptotic rates before you go to supercomputer scale, essentially 10 to the 9, 10 to the 10 unknowns. So of course, you really don't see the asymptotic convergence rates. So what we need to do is then to work on the implementation to have efficiency per degree of freedom. What we really want to do to have efficient high order methods is that the cost per unknown should be similar as in a low order method when you go to high orders. So that's really the important factor. And this is where we come to software. As we come to doing this in the deal.II library. So let me just start with saying that we have this library approach in our group and within the deal.II community. So deal.II is a software which is providing us with a finite element infrastructure. I think there's many FEM people here which very well know how you can make the split. And when we write application codes, for example, the code that does the simulation of CFD, this is called XLDG, a code developed in our group and with partners. This would be sitting on top of deal.II. We have other applications targeting different scenarios where we could create a different setup here. Now, deal.II, of course, is a library which focuses on finite element methods, including matrix-free algorithms that I'm going to discuss a bit later. But of course, we have other libraries sitting underneath it. We're going to use Betsy or Trilinos for linear solvers, maybe. We use Hyper as an algebraic multigrid preconditioner in certain contexts. We have meshing libraries like Metis or pForest or similar techniques. And eventually, all of those libraries are also going to be building on top of other software layers. For example, when we think about the hardware, we have GPUs on many supercomputers today. So we have different architectures like NVIDIA GPUs with CUDA, we have AMD GPUs, we have Intel GPUs, maybe have CPU systems where we use SIMD, this as a single instruction, multiple data paradigms. And of course, we have MPI to span multiple nodes. So there's a lot of issues in terms of the software layers, and deal.II is not solving all of them. It really tries to focus on the important parts. So I told you that we use this CFD code where we do our CFD equations. So deal.II does not implement the Navier-Stokes equations. deal.II just provides us kind of how do derivatives of finite elements look like, how can we use vectors, how can we partition a domain, and so on. So XLDG is the one which implements the equations, the physics, you could say, building on data structures from deal.II. Of course, we control the simulation by having iterative solvers, multigrid, and so on, that we kind of selectively call for the various operators, like the splitting method that I showed you before. And we also developed deal.II. Of course, deal.II is the library where we target the particular hardware. For example, we have some specialization for SIMD, for the CPU systems that we worked a lot on in the past. We have CUDA for GPUs on NVIDIA, and we have similar techniques. I told you before that we also have this kind of layer that we go through in Cocos, so there's a lot of additional things. We parallelize the mesh via deal.II, of course, using additional software. We go to that libraries like Trilinus or Betsy, and eventually we always have this kind of balance. So sometimes we start developing something in XIDG in the application solver, but then we see that this is generic functionality, so we pull it back to the deal.II library. Always trying to separate the concerns, kind of what is finite element, generic finite element functionality that we could put into deal.II, what is a specific solver. And of course, we have this approach because we want to reuse the data structure, so we don't want to just reinvent everything when we look at a different application. The deal.II library, just very quickly mentioning it, so this is a software library which has its name. Deal comes from differential equations analysis library. We have a classical project page. We have various elements, continuous, discontinuous, H-curl, H-diff elements. We're mostly having hexahedral elements, but we also have tetrahedral elements and mixed meshes at this point. We have some own linear algebra, and we have some linear algebra with Betsy, Trilinus, and all packages which sit behind Betsy and Trilinus. An important part for efficient implementations are matrix-free methods. Matrix-free methods are very attractive because you say that you don't build the matrix for solving the linear system, but we just apply the matrix onto a vector. So this goes well together with iterative solvers, where this is kind of one of the main operations. And the idea to say a matrix-free solver, I mean, here I just had this kind of gather operators where I just say how I would assemble a global matrix A and eventually apply it. And when you do matrix-free, you just run the element loop in the iterative solver. So this is kind of from a software perspective, not so interesting. The reason why we do it is that when we apply the discretized operator from the finite element integrals, we redundantly compute those integrals. You could then argue if it's more work to do than building a matrix. I mean, the traditional training 20 years ago when I started learning finite element methods, I was always trained you should avoid redundant operations, always compute something and store it somewhere. But matrix-free methods are the opposite. You just say that I recompute things over and over again. And actually, I don't even compute the local matrix AE here, but I also apply this by the integrals. Of course, it means that there is a restriction on preconditioners, which I want to touch in a few minutes. Let me first just mention that the operator evaluation matrix vector product is really, really efficient. So you see here a comparison of different operators. You see that the sparse matrix is listed as the throughput as a function of the polynomial degree. It's the orange line here. And for linear finite elements, the matrix is not too bad. But when you go to matrix-free algorithms, which are the three other lines, now they are on three different grid kinds. There's a DG method, which is the blue and the red line, and then there's this green line, which is the continuous finite element method, considering curved geometries where you have actually metric tensors on different orders, but then you also choose affine meshes where, of course, you can do additional tricks here. The bottom line of this slide here is that when you do matrix-free methods on a polynomial degree 3, for example, they provide you around a 10-time improvement in the operator evaluation time for this polynomial degree. If you check and compare linear finite elements, so linear shape functions, using a matrix, and you compare it to a high-order matrix-free implementation, then you see that even though you use high order, and everyone was trained to say that high order is more expensive because the coupling is more dense, a matrix-free solver will typically see an improvement in throughput, which is because the finite element integrals are kind of amortized across the degrees of freedom within an element. And the higher the degree, the more amortization you have work within the element. So this is a structure which is nice. So this is a CPU system. You would see very similar numbers on the GPU system. Okay. Let me now come to solvers, Navier-Stokes equations. So this is where we want to go. Matrix-free methods are providing good operator evaluation. You can use simple iterative solvers like conjugate gradient method with no preconditioner, or maybe with a diagonal preconditioner, where essentially the matrix vector product is dominating, and then you could do this. We've done this in the past a lot. We did a lot of benchmarks, some of them together with Sanyo and the other collaborators in the FEM library. But eventually you would need more sophisticated preconditioners when you use more complicated systems. For the Poisson type problems, again, you can use multigrid, which I mentioned before. We did work on multigrid methods where you can do Chebyshev smoothers around or Chebyshev iterations around the point-Jacobi method, which again is then dominated by the matrix vector product. You can do overlapping Schwarz method with fast diagonalization methods. So there is a few references from our group. Of course, there's many works with other people. For example, Paul Fisher and the NEC RS people in the US have a lot of results on this topic as well, but I just mentioned a few of the works that we did. So this is also well understood. But for the other operators in Navier-Stokes, the situation is not so clear. If you do the splitting method, we have the Helmholtz-like equation where you can do the diagonal. This is okay. But I want to focus today on one of these operators, which is this penalty step. I said before that we introduced this to kind of enforce this HDiff conforming property, so kind of imitating Rabi-Atomar, but we don't really do it for real. I mean, we can do Rabi-Atomar in deal.II, but I wanted to focus on this one because you can actually do it very efficiently. Now I just picked out these terms that we do in the penalty step here as a weak form. You see that, well, essentially what we need to do is we need to integrate over so we have this u tilde here, so we have an intermediate velocity, and then we kind of want to get the end of step velocity UH, which is subject to these additional constraints. Actually, just mention here, if you do augmented Lagrangian techniques for solving a coupled velocity pressure system, for getting nice Schur complements, you get similar operators eventually. But I just don't want to do into this direction. Let me show it again. So now we do this penalty step here, and if we write it as matrices, what we have is we have a mass matrix for the first term. So this is just kind of course, we kind of want to have the mass matrix, and then we want to remove the ingredients that we get from the divergence-free field here, and we want to remove the jumps in normal direction of the velocity field. When you look at this in 1D, kind of an imagination of kind of this field would be that I have block diagonal mass matrix. I have a block diagonal divergence matrix because we are discontinuous ansatz space. So we have discontinuous functions. Every element has its own divergence term, but this continuity over the element boundary, so the jump of the velocity, of course, introduces off-diagonal terms here. And this is an interesting system. I really like this from a linear algebra perspective for two reasons. Because the system, I mean, it looks very innocent. The matrix is not super complicated. It is symmetric, at least, so we can use conjugate gradients. But it's actually not so easy when you start thinking about it, because what are these penalty terms doing? Well, we essentially want to eliminate those parts which are disturbing. And eliminating something penalty methods, they use large penalty parameters. And if you think about iterative solvers like conjugate gradients, the convergence depends on the condition number. And if you penalize something, you put a large eigenvalue on those components that you want to get rid of, and you have eigenvalue 1 for those you want to pass through. So this is the problem here, right? We have many small eigenvalues to the unconstrained degrees of freedom, I call them. So the degrees of freedom which I want to keep, what I want to preserve, and they have the large eigenvalues for the ones that I want to eliminate. Of course, coming from the fact that the divergence matrix is singular, if you think about a three-dimensional system, you would say the divergence is, of course, addressing 1/3 of the eigenvalues. It's going to have large eigenvalues, and the other ones in the AD matrix are going to be 0, because it is kind of all divergence-free fields, which are 2/3 of all velocities which are possible in a space, are going to pass through. And then they have this large parameter. And now you could just say, well, how do we precondition this block here? So what we want to do is we want to have a cheap inverse of this matrix, AM plus AD plus AC, or ACI. So I do element-wise inverses, so I skip the off-diagonal terms in the continuity penalty here, which is reasonable to do because it's not so strong, so you could capture most of it. I will show you iteration counts in a minute. But when we do element-wise inverses, you could say that this is then a classical block Jacobi preconditioner. But the exact inverse would be way too expensive. If we have polynomial degree 4, we would have 375 degrees of freedom for every element. just to give you the math here, when you compare this to the matrix factor product in this operator, it's about 100 times slower. So this is not something you want to do. You don't want to use matrices in high orders. And the polynomial degree 4 is maybe not even the highest order. It's just matrices are not good for high order. I think many in the audience know this. The other option you could do is you could choose the simple preconditioner just inverting the mass matrix, because mass matrices are easy to invert. You don't need to build the full matrix. There is some techniques that we did. I mean, there's other techniques. I mean, it's essentially just saying that, I mean, mass matrix could be approximated well by the diagonal, or you could just transform to the diagonal basis, so kind of transforming to the Lagrange polynomials in the quadrature points for a quadrature formula with the same number of points as you have shape functions. You could transform into that basis, apply a diagonal basis there, and then transform back if you insist on another finite element basis. However, the mass matrix inverse, it's of course cheap to apply. It works well if you just have the mass matrix and the divergence constraint. So just the first one. Why does it work well? Because the divergence constraint, I told you that it leaves 2/3 of the eigenvalues unaltered, and just 1/3 is captured. And when you apply the mass matrix, you have all the eigenvalues related to the degrees of freedom which are kept. All of those are 1, exactly 1. So you have a very nice clustering of degrees of freedom. And again, for clustering, conjugate gradient works well. However, when you start adding this continuity constraint across the element boundaries, then you further constrain your space. And this further constraint on the space destroys the property, so that not all small eigenvalues are exactly 1 anymore. That's essentially the problem. And then we again get very bad condition numbers. So we have condition numbers which are 10 to the 6, 10 to the 8 or something because of the penalty factors. We need them for ensuring that the discretization works well, but then really get bad convergence numbers. Okay, so what we wanted to do is we wanted to develop a new solver. This is what we did. So how can we look at it here? I just have an illustration in 2D. Of course, eventually we do it in 3D, when we work on a real simulation. And eventually what we have is what you have the M matrix, the mass matrix, plus the divergence matrix, plus the continuity matrix. And when you check these matrices, they actually are tensor products or Kronecker products of one-dimensional matrices on a Cartesian mesh with constant coefficient, no deformation. But this is really the approximation we want to do. So this is the mass matrix in tensor product form, vector problem, of course. This is the divergence matrix. You see that this is the singular nature. You actually see this from the ingredients that go into this matrix. And then we have this continuity penalty term for the factors that are actually related to the element. You see that this is again a block diagonal matrix with just on the diagonal block something. But the G matrices are actually, if you choose the Lagrange basis, which is having nodes on the boundary, then the G matrix is just kind of a selection matrix on the left and on the right boundary. So this is just having 1 or 2 entries. So just in the 1, 1 and n entry. You have an entry, everything else is 0 in the G matrix. But it's ill-conditioned again, because it has large eigenvalues compared to the mass matrix. And when we want to compute the inverse of this matrix, well, we had to do 2 things. The one thing is that we actually collect the continuity penalty, the last matrix, with the first matrix, so that is my times ax here. So ax is now collecting the mass matrix and the G matrix here for this kind of boundary term. And then we keep the singular matrix as a separate term here. And once we have those matrices, we can start applying nice techniques here. What we do is that we actually say that, well, this kind of first matrix, which is block diagonal, we can use tensor product inverses for this one. So this is easy to invert, because essentially tensor product Kronecker matrices inverted are just inverting the factors. And then we're saying, well, actually the second term here, this is just some rank n here. So this is a low rank update here, because eventually the rank of the divergence matrix in 2D would be half of the size of the full matrix B. So this is a low rank in my books here. In 3D, it's actually even more than this the C times C transpose terms here that we have in the update. This is 1/3 of all eigenvalues. So this is low rank. And low rank inversions, you know how to do it, right? Or at least those familiar with linear algebra know is there is a formula which is called Sherman-Morrison-Woodbury formula, which tells us that if we have a rank K update to a matrix B, then we can have an explicit formula for this inverse. And this is the formula that I have down here. So if B is the matrix collecting the first one, and then we just need to invert the B matrix sometimes here, and then have this inner matrix, identity matrix minus C transpose times B to the inverse times C. And this one I have to invert. And it turns out that actually all of these ingredients that I need to go into the inverse of this matrix, they are again Kronecker products of 1D matrices and sum of Kronecker products where I can use fast diagonalization, similar techniques as we use for inverting the B matrix in the first place. This is a known problem. We trace it back to that one here. Now we can go into business. Everything is a tensor product, at least on Cartesian meshes, and we can start evaluating. We evaluated this on a channel flow, so this is a typical turbulent test problem, very simple. I just want to give you some illustration here. If I use a penalty factor of 10 times the velocity and some mesh scaling, depending on what exactly of the two terms are you using, I have polynomial degree 5. If I use no preconditioner, the conjugate gradient method would not converge in 1,000 iterations. So I mean, without preconditioner, this kind of huge condition number of large eigenvalues to the penalized terms and the small ones are just making you explode. If I use mass matrix as a preconditioner, I get around 20 iterations per solve, averaged over 100,000 time steps. So this is a nice solver, but we actually wanted to improve the efficiency. And just to show you how efficient you can be with this proposed preconditioner, I get 5 iterations, or 4.7, averaged over the same time span. And why do I get less? I mean, I don't get 1 iteration because on a Cartesian mesh, you could say that the block diagonal is actually 1. However, I told you I ignore the off-diagonal matrix contributions to the divergence to the continuity penalty, because I just want to invert element-wise matrices. I don't want to cross the other elements. So this is why I still need some iterations. And then there is also some approximation that I'm doing because I don't want to store a separate matrix for every element, but I just want to approximate it near the boundary. I have some small errors that I make. The throughput is a bit less. So if the throughput now I count for one CG iteration, throughput is a bit less than with the mass matrix, but overall, since I only have a fourth of the iteration count, I'm like around 3 times faster with the solver, which is making me very happy. And of course, we do multigrid also now. Just to conclude my talk here, we have running multigrid solvers on large scales. I mean, this is Supermucker machine in Germany, which is not so large anymore, but we are targeting a new GPU system in Germany, Jupyter, which is upcoming in the next months, where we're trying to do more efficient solvers, of course. I mean, we have done a lot of multigrid flavors, essentially, and they work pretty well with matrix-free methods. They work well with high orders. I have this graph here where we just illustrated a benchmark in CFD community where we just showed that normalized for certain computer architecture, we can be 1 to 2 orders of magnitude faster than most other codes that publish the results. Of course, this is some years back, but I really think that we did a good job here in terms of accuracy over runtime with these solvers. And we're always trying to continue working. And to conclude, I just have a few slides on the last topic that we worked on in our group here, which is cut finite element algorithms. I think when I told you that we use hex meshes because we like the performance, I should have said that meshing is complicated with hex meshes. And one of the directions that we're investigating, besides the fitted meshes, is also unfitted meshes. So unfitted meshes just uses some level set function maybe. In deal.II, we often use adaptively refined meshes near the interface because the interface region is really what interests us most of the time. This is a Poisson problem that we solved, so this was for a battery, but it really does not really matter here where exactly we're working. We can use on the inverted domain here and do CFD simulations as well. It's a nice application for high order methods, I should say, because it really is smooth near the boundaries. I mean, the boundaries are well represented, especially for complicated geometries. So this is a nice application. However, when you do cut finite element methods, you don't fit the boundary to the computational domain, but you just let it cut through the elements. You need specific quadrature formulas to integrate on those. And then you see it on this illustration here, they're not forming tensor products anymore. And when you lose the tensor product of the quadrature formula, you kind of lose the benefits of sum factorization, which is kind of one of the key ingredients that makes matrix-free methods fast. Just to show you a difference here, this is a transport problem in 2D and 3D. You would say that if you use polynomials of degree 5, with sum factorization, I spend around 100 arithmetic operation per degree of freedom. If I don't use the tensor product, I spend 3,500. So there's a factor of 30 or more than 30 in terms of the arithmetic work. So there's a lot of work to do when you do unstructured tests. However, you can do matrix-free methods for those as well. And it actually pays off to still do matrix-free, as we could show in a preprint and hopefully soon be published. What you see here is continuous elements on the left, the G elements on the right. The classical matrix-free methods are the upper bound here. there is the matrix-free methods just not using the structure are the lower bound here, and then you see that the matrices are most of the times lower. Maybe not for linear shape functions. Linear shape functions are pretty good with matrices. However, high order shape functions are really not efficient with matrices because of this dense coupling. And it's interesting that when you recompute the integrals without using any structure in the quadrature formula, so without the sum factorization algorithm, you can still beat the matrices by a factor of 5 to 10. There is a lot of work to do for our group. I mean, we have these operators for solving cut finite element. In the cut elements, we don't have nice inverses anymore, so we cannot do fast diagonalization, and we need to figure out how we can do a fast solver for that part, for example. With that, I would like to conclude. I hope I gave you some insight into fluid dynamics simulations that we do in our code, how we do it in the deal.II library, and some iterative solver developments that we did. Thank you very much.
All right. Thank you very much, Martin.
Yeah.
For the excellent talk. A lot of interesting stuff. We lost you there for a second, but you came back. I believe everybody can hear you now. Okay. Any questions for Martin? Please just feel free to unmute and ask.
Martin, I have a question about your projection method. My understanding is that this is a Turing type projection method in which you solve the Poisson equation for the pressure rather than for a pressure correction. And my question is, the splitting error of this method is probably first order in time. And the question is, does this time error pollute the accuracy of your high order finite element space discretization?
That's a good question. I should mention that the particular projection type that we use, this is actually belonging to the, so here it is, sorry. This is actually belonging to the incremental type of projection methods. So this is actually a high order one because of the kind of the extrapolation from the old time values. Essentially, this can be as accurate as the PDF method. So you can do PDF2, so you can do second and third order accurate methods. So there is some incremental version of this one. So this is not a classical pressure correction where the Gerard type method, this is kind of using the momentum equation in the first equation as well. So in that case, you would actually see first order accurate method. But the kind of this particular splitting, so where you essentially do the pressure between convective term and viscous terms, this is actually a higher order accurate splitting here. So in this case, it's not so bad. I mean, you have this specific boundary condition. I mean, of course, there is still some limitation. The problem is that you only have conditional stability. Well, of course, because we also have the convective term explicitly. But you can show that you can actually do this method second order accurate in time. I think you can do third order accuracy in the velocity, not in the pressure. I think in the pressure, you're limited by second order. But just to answer the question, if I would do first order accurate time integration, I would definitely see it. I would not recommend this one.
Okay, I see.
Second order and third order is okay, but first order accurate would definitely destroy your spatial discretization.
Well, since you're showing the boundary condition, may I ask if you still have no penetration on solid walls? Because when you, if you're using this boundary condition, which looks like consistent PP boundary condition, so when you add the pressure gradient, well, suppose that your intermediate velocity, the normal component of your intermediate velocity is 0 on a solid wall. But then you're using this pressure boundary condition, and this means that the normal component of the final velocity will not be 0 on the solid wall.
This is correct, yes. I mean, or at least it is not 0 after the third step here. So when we do the projection step, it's not 0. When we do the viscous step here, for the viscous step, again, we would impose the boundary condition, and then it kind of comes back again. And I mean, this is on the order of the discretization error.
Okay, so the question is, which is the real velocity, like U hat or U double hat?
This is kind of one of these reasoning that you kind of know from projection methods. I think we're well aware of that one. I mean, I think the question is, I mean, I would say that with discontinuous spaces, you're not so affected with it. Of course, they're always having subject to some discretization errors. In my opinion, I would just say, well, the UN+1 is a valid velocity here. Of course, then always saying that, well, I do some violation in one of the factors, but actually in this one, I think this is the nice thing about this velocity correction that you see here, that this one is not as bad as the pressure correction methods, which are more common, because in pressure correction, you really have to decide if you want to have inconsistent boundary conditions or divergence-free errors. Whereas in this case, the third step actually does impose the boundary condition, but it also preserves the divergence-free condition, if I remember correctly. But I could look into it more precisely, or we could discuss at some other occasion.
Yes. Okay, thank you.
You're welcome.
All right, thanks for the good question, Dmitry. In the CAD-FEM work, you mentioned that, and I think you kind of briefly mentioned that you're using Robert Say's algorithm, probably
Yes.
other
Yes.
2 points. And you said they can't be tensor product anymore.
Yes.
That's right. There's no way to use tensor product quadrature.
I mean, the point is like this. I mean, there is, of course, like, I mean, Say's algorithm, it actually is not completely structured, without structure. When you look closely at this figure, you see that it's kind of composed of some deformed tensor product. So essentially, it's tensor product in 1 or 2 of the dimensions of the three dimensions in a 3D problem. So you could, of course, use the substructure to some extent. Yes. I mean, it's a bit more complicated because you lose it partially. Of course, you could then think about different alternatives, just kind of because the Sayé algorithm, I mean, it essentially is a transformation. So you could think about this is a local deformation of the element, which essentially just is an additional Jacobian that you introduce somehow, that you could also use for optimization. So I'm just saying that I think one could do better. Yes, we did not do it yet, but this is an alternative. There is also different methods, though not using this kind of implicit function theorem as Sayé's method is doing, but you could use moment fitting techniques which don't displace don't move the quadrature points, so they keep them just where they are in the regular elements, and then modify the weights instead. You could use those as well, but in our opinion, that this kind of moving the points is a more accurate method. But of course, as I'm saying, I think you could recover some of the tensor product by additional deformations. It's just that we did not use them yet.
Yeah. Okay.
It's an interesting field, I would say.
I agree. All right. Other questions for Martin? Do you have any experience with, so a lot of the stuff you presented is for tensor product elements, which is what we kind of all are focused on. But do you have any experience with simplices and how are the methods and doing all of this on simplices?
I mean, we do some work on simplices right now as well in one of our projects. So I think I have some insight into them. I mean, what we typically observe is that, I mean, when you compare them on a degree of freedom basis, then simplices are between a factor of 3 to 5 slower per unknown than the hexahedral element shapes, approximately. Now, of course, it depends a bit on which algorithm you choose, but if you use low order simplex methods, low order up to degree 3 maybe, then you would typically choose the full interpolation matrices for a matrix-free algorithm, so you don't use any structure. And in that case, maybe it's a factor of 3 to 5 slower per unknown than the hexahedral elements, which, I mean, it sounds like quite a lot, but on the other hand, I mean, you can use arbitrary meshes, and I mean, if you do a hex mesh with a bad element quality, then your CFL condition is much more reduced than a factor of 3. So in that sense, I would say that, I mean, it's not too bad. I mean, we have, at least that's our experience. The other thing is, if you go to, instead of using simplex elements for higher degrees, you could also use this embedded tensor product. So essentially kind of having this nectar plus approach. What they are doing essentially just having collapsed tensor products and expanding it during the evaluation, where I also think that you would probably lose a similar factor, maybe 3 to 5 as well on intermediate degrees, like say degrees 4, 5, 6 or something like that. I don't know what your experience is, but my experience is that they're slower, but not so by such a big extent that you would just not use that meshes at all. I mean, my preference would be, of course, if we have complicated geometries, to use mixed meshes, X-dominant meshes, if we can. But I mean, I guess there is a lot of work in the meshing community also. I mean, they have a lot of issues to struggle with.
Well, since you brought this up, what about the pyramids in the mixed meshes?
Oh yeah, well, I mean, they're partly tensor products, so at least.
Okay.
But that's maybe something we should discuss in another occasion. I mean, I definitely think that we could do better there, and I mean, I'm looking forward to see how the community moves towards these more general element types. But I think there is work that we initiated in deal 2. We don't use the tensor products in pyramids right now, But eventually, when we kind of do it more regularly, I think we at some point have to. Well, I don't know, maybe, but this is what I envision.
No, I agree. I agree. It's interesting, and I'm also curious to see how the community moves. Other questions for Martin? Please feel free, if you have any questions, feel free to, don't be shy, feel free to unmute and ask.
I have a question.
Go ahead, Victor.
So your Taylor-Green vortex problem, so you showed a plot of, I believe the relative error of the kinetic energy decreasing as a function of the number of degrees of freedom.
Yes.
By any chance, do you have, maybe you've plotted this and maybe it's not in your presentation, but do you have a sense of the turbulent kinetic energy spectrum as you increase the order? What is that doing as far as capturing the small scales of your turbulence? Do you see you're able to capture more of those small scale features?
Yes, I mean it's definitely the general observation is that you capture more of this more scale turbulence. Yes, I mean there is some issues with the high order discretization, at least with the basic discretization methods. I mean some people call it kind of the kinetic energy bump. So essentially, kind of just because of the dispersive properties or dispersive dissipative properties of high order G methods with upwind fluxes, you kind of get actually kind of getting too little dissipation on some of the scales. So it actually is not so that if you look at this log plot of the kinetic energy over the scales, then you don't see a perfect, I don't know, 5/3 reduction, which is a typical slope depending on which configuration you look at. But you see kind of some additional damming up of the structures. But you definitely see that high order methods are having a larger scale of good kinetic energy content on the scales than a lower order method. Even though, of course, I would say that it saturates with degrees 3, 4, maybe 5. I didn't see a big difference. I mean, I don't have the numbers exactly in my head, but what I remember is that going from polynomial degree 2 to 5 is definitely improving things, but above 5, it's not so much anymore.
I see. Okay, so there's like a sweet spot that you're not.
I would think so. I mean, of course, there is different sweet spots depending on different configurations. Taylor-Green is just a simple case, but I believe that, I mean, again, this is very personal opinion. I'm more believing into degrees 3, 4, 5, maybe 6, 7, and not so much in 10 or 15, even though we do it in this particular figure, but I don't really think that the highest orders are the most interesting ones. But of course, there's different applications with different needs possibly.
Got it. Thank you.
You're welcome.